Yeah, good morning, everyone. We're just waiting a couple of minutes for people to join, and then we'll get started with the event. We'll just give it another minute or so. I can just see some people connecting in. Okay, I think we've got a fair few people that have joined us now. Thank you for joining us this morning for our additive manufacturing event, focusing on the blue economy with a particular amount of presentations looking at wind turbine blades and opportunities for additive manufacturing going forward. My name is Neil Farrington. I'm going to be running most of the event today and trying to control the presentations where I can. I'm going to give you a bit of an introduction to the PERISCOPE project and the overall agenda for the event before we move into the fuller sessions and the presentations. So thank you for everyone for joining us today. I'd also like to mention that we will be videoing the event, so please let us know if you have any issues there. We'll also be monitoring the chat function throughout the event. So if you have any questions or comments you wish to add, please feel free to do so, and then we'll seek to address those issues, concerns, questions that are raised as part of session 3. So just moving on to the agenda for today, it'll be starting with myself. My name is Neil Farrington from the Offshore Renewable Energy Catapult. We're going to then have some further introductions to the project and the subject area. We'll have a quick coffee break at 10 o'clock and then move into session 2, where we start on some of the more technical content, looking at the opportunities, challenges and potential future projects for additive manufacturing. And again, we have a particular focus on wind turbine blades there. There's a crossover with some other ocean energy technologies. The sessions coming in at 10:10 start with Mark Forrest, who's our blades team leader at the Offshore Renewable Energy Catapult, that will be focusing on sandwich cores. We'll then be moving to look at interlayer adhesion, different issues in that area and impacts on additive manufacturing. We then have a quick session from Dr. Ajit Panesar from Imperial College London that will be giving us an overview of their activity around design, machine learning and topology optimization. The final session 3, we're really hoping that'll be a nice collaborative session where we can start to understand some of the interests of the audience, questions and queries you have, and potential opportunities to collaborate on future projects going forward. So again, please feel free to log questions and comments in the chat throughout the event, and we'll pick those up in session 3. So just coming in with a bit of a background to begin with, PERISCOPE is a Inter-Reg North Sea Region project that has been running the last 3 years with an ambition to create a permanent ecosystem for innovation in the blue economy. The Catapult has been involved over the last year or so, as well as looking at future foresight and technology evolution in the blue economy. The Catapult have particularly been focusing on 2 deep dive subject areas, where we're putting quite a lot of activity to understand market opportunities for 3D printing and additive manufacturing, hence the event you've all joined today. We're also running a second event on the 25th of February that has a strong focus on robotics and autonomous solutions in the offshore energy sector. And again, the ambition here is to understand the current market position look at key areas for innovation that can be taken forward, potentially with a collaborative approach with businesses, SMEs and research institutions across the North Sea region. And we'd like to thank PERISCOPE for funding the event and the activities today. I also wanted to provide a quick thanks to the Marine Eye programme that has helped us reach out to some of its network and members. The Marine Eye programme is an ERDF funded project running down in Cornwall in the southwest UK. A whole range of technology and marine innovation projects, right the way through from autonomy to looking at different vessel designs, for example. And we have some particular exciting activity happening there, focused on floating wind development in the Celtic Sea. And hopefully a funding opportunity coming up soon to start looking at the whole sector and breaking down materials content for blades, towers and foundations, and to start to map out a potential avenue through for low carbon content within those materials. And we're hoping additive manufacturing will have a key role to play there. I also wanted to thank the Ocean Power Innovation Network that has again been very helpful in promoting the event to their members. OPIN is a 3.5-year EU-funded initiative operating across Northwestern Europe with the aim of evolving cross-sector collaboration and cross-regional partnerships, again to accelerate developments in the offshore renewable energy sector. OPIN has a number of interesting services that some of the audience may be interested in, offering direct technology assessments, again all the way through from floating solar companies up to our first rocket pack manufacturer that we'll be meeting next week. We also have a number of collaborative innovation groups focusing on key areas of interest around corrosion and anchoring and mooring, for example. OPIN is a free network. It's available to next year. And again, pop on the website if anyone's interested in joining. OPIN now has 397 members across 27 countries. Finally, I just pop my contact details up there. So again, I'll generally be coordinating the event. If anyone wants to come back to us afterwards for more details, discussions, or to talk about project collaboration opportunities, please get in touch. So I'm now going to pass over to Tom Wildsmith from the Offshore Renewable Energy Catapult that's going to give us an introduction to Catapult activities, RD&I interests, and project development around the AM sector. So over to you, Tom.
Hello, everyone. Yeah, so I'm Tom Wildsmith. I'm very fortunate to work with the technical team that are presenting later today. So I wanted to give you a quick overview of the Catapult and what we do. So I won't take too long here. So the Offshore Renewable Energy Catapult is a UK-based technology centre looking at how we can accelerate creation and growth of companies and jobs, particularly in offshore renewables, so offshore wind, wave and tidal. And that's how we tie in nicely with a lot of the work that's going on in the southwest with Neil. We've got a range of facilities. We bring together innovators, industry and academia, and we really are, again, focused on how can we reduce the cost and risk in renewable technologies with a viewpoint of how we can support UK businesses. But we do work internationally. To give you an idea of some of the work that we've done or carry out, in the last year that we have a full record, we worked with over 200 SMEs on over 60 international projects. We have in excess of 250 academic collaborations, and we're working on product development projects. We had 44 in that year. We've got over $250 million valued test facilities, primarily based in Blythe in the northeast of England, but also including our own turbine in Scotland. So we have now 200 engineering, research and sector experts spread across the UK. So we have 8 regional centres. So our head offices are in Glasgow. We've got, as I mentioned, a strong test and validation component in Blythe. But now we have reach across the majority of the country, working in the likes of Lowestoft, Pembroke, and all the way down in Hale, and all the way up in Aberdeen. We've got 3 UK academic research hubs. So we're working with the universities of Manchester and Strathclyde on electrical infrastructures. We work with the University of Bristol on blades. and the University of Sheffield on powertrains. And a couple of years ago, we set up an International Research and Innovation Centre in Yantai in China, which is very much looking at how we can support UK businesses entering into the Chinese market. So the role of the catapult, I think this is a really nice diagram to explain what we do. We sort of act in both directions. So we work with owner operators and OEMs, identifying challenges and working down the supply chain, looking at what we can do to find in the tier 1 SME and innovators, or even in the academic base. But then we also try and de-risk innovations going up to those OEMs. So supporting SMEs in their developments, trying to help enable entry into tier 1 or entry into the OEMs through test and validation or research activities. So yeah, it's a really exciting organisation to be part of. We do a huge amount of different elements of work, and this sort of snapshot hopefully gives you a quick indication of what we're doing. We're broken into roughly 3 technical directorates. So all of the work that's been presented today is coming from our research and disruptive innovation team. So the main focus within that team is to try and find the innovations which are close but not commercialized yet. So we're working, above academic research, but not quite at commercialization. So TRL 3, TRL 4 onwards. And we evaluate and work on a range of technologies. Today, we're very much focused on materials and manufacturing, and again, looking at blades and composites. That feeds nicely into the test and validation aspect. So here we're looking at next generation turbines and balance of plant, and the design and validation and component testing. These tend to be much higher TRL, TRL 6, TRL 9, working with OEMs, working with people who've already manufactured or at least got designs in place to manufacture. And we're really looking at, what can we do in order to ensure long lifetime of components? What can we do in terms of certification? How can we get them to the point where commercial sales can be realized? And the third element is our operational performance directorate. Here we're really looking at what's happening once the turbine is up and running. So again, how can we reduce operations costs? How can we reduce the amount of time spent offshore? How can we support SMEs in that space? Again, a really interesting and exciting opportunity in the UK, given the volume of offshore wind that we have now and the targets we're working towards. So our focus is around delivering UK impact. I think this is a nice slide in terms of what we're trying to do. I think it's always nice to show some ambition. So we're aiming by the end of 2023 to have supported over 750 SMEs and brought over 60 products to market. That's a real challenge for us and something we're really striving to do. So the team today, as I mentioned earlier, very much focused on materials, on blades research, and on composites. So I think then now is a good time to hand over to Oliver, who's going to give an overview of the work that he's been carrying out alongside Mark. So Oliver, if I can pass on to yourself.
Sure, thanks. Everyone see that all right?
Yeah, just need to drop it onto presenter view, Oliver. Perfect.
Cool. Yeah, so I'm Oliver. I'm going to give a sort of overview really of this section of the PERISCOPE work that we've been carrying out. So we've carried out a sort of like a deep dive into the literature as a sort of benchmarking kind of study to see where sort of the gaps are in additive manufacturing research, and see really sort of where the kind of research opportunities lie in the overall scheme of things. And I'm basically just going to talk about kind of the outputs of the report and what I think that it's sort of telling us, implications on the manufacturing scenario, and highlights for kind of like future work. So what's that saying? So the aims really were to really do a deep dive into the literature, see where the sort of current state of the art is, and like basically sort of types of common practices that people are carrying out, and to sort of really kind of it's more of a taking stock kind of exercise, current state of the art, where the gaps are, and to identify sort of common research themes that sort of facilitate the route to market using additive manufacturing. It also kind of looks at sort of determination of sort of the applications of additive manufacturing towards the wind industry and the blue economy, so like tidal and vessel technology as well. So really it's just to get a lie of the land and to see what sort of research directions should be pursued. I think there's many different sort of additive manufacturing technologies that are kind of available, but we sort of focus more on the sort of FFF, so sort of fused filament fabrication slash FDM, so that sort of methodology, which is possibly more suited to the structural applications due to larger AM platforms coming to the fore. So that becomes a bit more of the focus towards the end of the report. It's really just trying to highlight the advantages and the kind of opportunities as well of using larger scale additive manufacturing methodologies in the kind of context of renewables. And so towards the end of the report, the outfall was we sort of provided a brief overview of the current commercially available systems that are available for purchase. So the kind of rationale, the main rationale for additive manufacturing in terms of sort of the thermoplastic extrusion is kind of higher throughput, reduced lead times. So higher throughput. So you're going from the desktop printing, which is you're talking grams an hour, to kilograms an hour in larger additive manufacturing platforms for thermoplastic extrusion. You got sort of easier migration from the CAD design through to the part. It's a much quicker process. So you have your original CAD file, and then convert that to an STL, and then to a G code, which basically forms your tool paths. Midstream changes are somewhat easier than conventional manufacturing methods. It's thus easier and cheaper to also repair parts via subtractive machining, and due to the reversible nature of thermoplastics, can be reformed. So reduces scrap and that kind of thing. There's much greater design freedom, especially using sort of multi-axis robotic systems with the thermoplastic extrusion system on the end as an end effector. It's tempting to say that it reduces like a lot of intermediate steps, but it doesn't completely eliminate intermediate steps, but you got potential to reduce some of the subtractive post-processing steps if done correctly. I think the obvious sort of cost saving as well as reduction or practically elimination of traditional manufacturing consumables. So like tapes, bagging materials, that kind of thing. So the original barriers to market penetration historically were sort of throughput, cost, and part size is sort of mostly removed with these larger additive manufacturing platforms, but I still see it as there's still a lot of open goals with regards to research opportunities as well. So this is just going to be a brief overview of the process. I don't want to get into too much detail here, but so the overview of the process of thermoplastic extrusion, I've called it sort of fused deposition, fused filament fabrication, but it's technically not. If we're being a bit more looser about it, it's probably preferable to say thermoplastic extrusion type methodology. So in general, most additive manufacturing process involve like some kind of layer by layer build up of the part in the upwards direction, in the Z direction, via sort of melted. So the extruder melts thermoplastic material, and then you get a layer by layer deposition of a bead or a road, it's sometimes called, and then that gradually, as the beads get built up, so that the part builds up in the Z direction. So each bead is deposited on subsequent beads, forming the part. So ultimately, the sort of extruder follows a kind of tool path, which is obtained from the G code, similar to like a CNC machine. So yes, basically most AM technologies sort of focus are sort of based on this type of layer by layer build. The extruder usually, in the case of a gantry system, will move in a lateral XY position, sort of motion. However, if you have a 6-axis robot, you have much more complex geometric flexibility. So you're not limited to the a lateral XY movement or motion. So you are able to produce curved parts, for example. Larger additive manufacturing platforms that are for sort of thermoplastic extrusion tend to use pellets instead of filaments. So that drastically reduces material costs. So typically, if you were going to do an industrial filament bed 3D printer, your material filament, in the case of ABS with 20% carbon fiber loading, your material costs are typically around $30 per kilo. It's going down to around $2 to $3 a kilo for, say, ABS pellets with 20% carbon fiber loading. So your material costs are much lower in the case of pellet systems, to which larger AM platforms tend to use. So kind of general applications, I think generally immediate applications, certainly in the case of the Windblade manufacture, mold production, and this is also the case for many other industries as well. It's sort of a bit of a get out of jail free card, but it's definitely imminently economical to carry out. Typical conventional molds in turbine blades have a lot of more laborious steps. So you have to manufacture the plug, which is the male mold to which the female mold is then formed from. So you've got the layup of the fiberglass shell, plus the inspection, plus the installation of the electrical systems, etc., etc. So that's time consuming. It takes around estimates to be around 27 weeks for a 50-meter blade at the approximate cost of just over $2 million. So Oak Ridge National Laboratory, ORNL over in Tennessee, have essentially shown that additive manufacturing is quite viable in terms of mold production in wind blades. So they've shown that they can produce via additive manufacturing, sort of thermoplastic extrusion. They can produce molds that are slightly undersized, and then they lay up some extra glass fiber to produce the sort of surface, and then they machine it to the correct geometry with sort of air channels for the curing system. And they've shown that it's approximately 650K per mold, which could be further reduced with better machine utilization. So I think this is a very promising avenue for research, but I I think it's also good to focus on sort of actual sort of load bearing structure. So this is more for indirect manufacturing. So some general applications in the wind industry. So I think there's sort of three sort of main kind of scenarios. So the imminent, like a first, I say a fairly imminent scenario could be the application in novel mold solutions, as just discussed. That would be sort of more of an indirect manufacturing approach. Moving on to sort of a direct manufacturing approach where you're starting to use thermoplastic, additively manufactured thermoplastics in minor blade components. So, for example, sandwich cores. So keeping the rest of the manufacturing process of the blade the same, and it's not too disruptive. I think Mark's going to be talking a bit about the sandwich cores in his slides later on, and then potentially much further down the line, you could be talking about sort of major blade components made from AM, so sort of entire sections and airfoils and out of additively manufactured thermoplastics. So as I was sort of saying, I think the initially, I don't think the AM methods are going to be applied to entire blades, but certainly it's an absolute open goal in terms of research opportunities in this sort of direction. I think in general, really, the sort of the key research areas that really ought to be focused on in order to facilitate uptake and sort of suitability. I think obviously sort of material development. So things like certification, and I believe also sort of standardization of material characterization methodologies for additive manufacturing. That's absolutely key. Process development for sure, and also sort of novel numerical FEA and sort of topology optimization tool development is going to be a requirement as well. Also metrology, so sort of how a part that's been produced additive via AM methods sort of deviates from its original CAD dimensions, and how you measure that and characterize that, and also inspection and NDT methods as well. Current research really so these guys over in ORNL at Oak Ridge have collaborated. They were sort of among the first to kind of really attempt to sort of upscale the thermoplastic extrusion towards like parts that can actually be used in real life, sort of the types of scale that we need. And they collaborated with Cincinnati Machine Tools, who are experts in high-speed gantry systems. And they collaborated over many years to produce this BAM, big area additive manufacturing machine. And they produced very, very high deposition rates, so around sort of 36 kilos an hour. It's a gantry system, so it builds upwards in the Z direction. And they've used a single screw extruder to produce ABS-based thermoplastic trim and drill tool for a wing skin of a Boeing 777X jet, which is just coming in the pipeline. And they've got many collaborators across the US looking at sort of larger scale AM parts. Also at University of Maine have collaborated with another machine tool manufacturer, Ingersoll, and they've produced a boat hull via, again, thermoplastic extrusion using a gantry system. As far as I'm aware, it's the largest printed object in the world to date, I believe, and it's it's a boat that's 7.6 meters in length. and about just over 2 tons, taking approximately 72 hours to fabricate. So very, very quick fabrication for such a large object. And their system is capable of around sort of just over 200 kilos an hour, which is very, very high throughput. So they've got, this is a prototype at this stage. This is a very big gantry system with a additive thermoplastic extruder with milling and subtractive processes installed on the machine as well. So their USP is sort of raw biomaterials and recyclable and sustainable materials for use in additive manufacture of large marine vessels. So they've massively helped the marine sector in the area and have basically been able to provide the initial capex to carry out this research. They've recently got a collaboration with ORNL in a government-funded project worth around 20 million for further research in looking at large structures in recyclable and sustainable thermoplastic materials. So I think research opportunities where we kind of ideally would like to start adding to the body of knowledge is that gantry systems don't perhaps offer the same geometric advantages compared with the multi-axis robots. So I think to add to the sort of excellent research that's already been carried out, the excellent body of research, multi-axis robot systems such as the one that we've recently invested in with SEAD offer really, really high quality design complexity for features, which will enable us to carry out sort of novel solutions in sort of foam and cores. So, for example, gyroid cores, which is another thing that Mark's going to elaborate on in his slides after this, in which we can tailor the stiffness along the part. Improvements in material strength is another key research opportunity around the current deficiencies around anisotropy, which I'm going to probably touch on in terms of the interlayer adhesion a little bit later as well. Current usage in mold manufacturing, I think that's something I touched on just a couple of slides ago. It's still highly applicable in Windblade, and likewise for marine vessels, among other industries. But ideally, really, it would be good to sort of shift more away from sort of indirect manufacturing approaches to sort of what are the sort of parts that we can actually produce that are going to be sort of used in secondary load-bearing applications. Another, I think it's very important to really take stock and improve sort of like material characterization methodologies. So currently we're using sort of ASTM standards that are for injection molded thermoplastics. So I think there's an open goal for research in the sort of material characterization that would enable better material certification, and yeah, understanding sort of methodologies in measuring the part and how they deviate from the tolerances, and that kind of thing. I think also going forward, in-process sort of closed loop kind of inspection in the machines that is capable of thermoplastic extrusion. So, for example, in-process sort of ultrasonic, for example, or detection methods that can detect whether the process is whether it's optimal or not, so that the machine can feed back the data back into the machine for sort of self-correcting in process. So I think that's definitely another potential route forward in AM. So without further ado, I think I'll pass over to Mark Forrest, who's going to be giving an overview of additive manufacturing of blades as a general sort of research avenue. So Mark, I think we're over to you.
Thanks very much, Ollie. I'll just share my screen. Can everyone see that okay?
Yeah, all good.
Great. Thanks very much, Oliver. Good morning and good evening, wherever you are around the world. And thanks for joining us. My name's Dr. Mark Forrest. I'm the Blades Research Leader within RDI. And today I'd really like to take an upper level look at the future for blade manufacturing. And in doing so, I'd like to look at three main areas. Firstly, I'll give a little introduction to additive research within the Catapult. Secondly, I'll give an overall future vision of where we see blade manufacturing go and how additive manufacturing has a role to play. And then finally, I'll outline the body of the talk will really be around what we've called Blade, which was a feasibility study. We looked at how we'd go about implementing additive manufacturing into blade structure. So I think it's fairly safe to say that with its origins in marine craft, blade manufacturing has only seen relatively incremental change over the last 30 years or so. And so there's clear opportunity, we believe, and a market gap with additive manufacturing for the next generation of blades. So within RDI, we basically have a submission, if you like, and that's basically to accelerate the UK's IP growth for the next generation of blade manufacturing. And we'll be doing that with three clear developmental objectives. Firstly, to manufacture blades faster and at lower cost. Secondly, to enhance turbine performance or annualized energy production. And in hand with the first point there, both of those points basically address or seek to lower the cost of levelized energy. And thirdly, to reduce environmental impact of blade manufacture, particularly around end-of-life issues. So as far as additive manufacturing for blades goes, the research that we're undertaking are both in the design, manufacture and testing of structures, as well as materials and process development. The candidates that we're looking for, immediate kind of implementation around the design and manufacturing piece, leading edge protection, aerodynamic add-ons. But really, we look to eventually in time develop blade subcomponents and really those components which enable a modular blade route for blade manufacture. In the materials and process areas, we're specifically looking around next generation thermoplastics for additive manufacture. And within that, more specifically, enhanced LEP material solutions, whether they be thermoplastic, metallic shields, or fiber metal laminates. As far as our academic outreach go, we instituted the Windblade Research Hub, which is a collaboration with the University of Bristol. This was instituted in 2017, and so far has supported 6 doctoral students and 5 years of postdoctoral RA activity. Specifically, those themes and research we've sponsored, which complements additive manufacture, are topics on topology optimization, basic load assessment of blades and their behaviors, and also the development of materials and process for AM substructure development. And as Ollie alluded to earlier, we've invested in a new facility. We basically put out a call to tender, to which CEAD BV has won. And this cell will basically be going live in June 2021. It's really to enable rapid development of new blade designs and technologies and demonstrate their potential. So within this, more specifically, the cell is a 7-axis machine, about 4 by 2 meters. So we'll be able to do 1-to-1 scale component builds as well as some scaled structure as well. So as it's a very general audience, I've decided to do a very top level view of conventional blade manufacture. And generally, you know, it's a multi-step, 16 distinct processes for conventional blade manufacture. You're usually looking at a blade metronome of about 24 hours for these larger scale blades that are being built. Our ideal is to, with additive manufacture, to basically coalesce this to 4 main processes within that 24-hour metronome. So how would we do this? As far as we're concerned, there are basically 6 main points that we have to sort of attain, which would have a vision of future blade manufacturing that would be suitable for uptake. First of which is segmented blade design. Clearly, there are advantages both in the market for OEMs that use a segmented blade from a manufacturing point of view, because it means, for instance, they could keep a root section of their blade, and then basically their product range would be adapted by changing simply a tip section, for instance, for the aerodynamically more significant part of the blade. Modular blade components, we really believe that form should follow function. And so those items that are particularly made of a different material or rely on a different process can be substituted in and out of blade structure. For instance, leading edges have completely different requirements than trailing edges, and spar caps and shear web components. But the heart of this concept is really, which is the holy grail, I guess, of additive manufacturing for direct manufacture. So we're looking at lower cost toolless manufacturing, where we're manufacturing parts directly without the capex burden of large tool sets, which, as Ollie has highlighted already, are extremely expensive, and they're very hard to amortize the blade cost against, blade per blade cost. The fourth most important point around additive manufacturing is the huge design freedom you can partake in. So particularly around aeroforms, and as you can see there, a winglet design, which is very difficult to produce using any other manufacturing technology. And that goes hand in hand with the fifth point there, which is to achieve mass savings. With topology optimization, there is large scope to take a lot of mass out of these blades, which obviously is a huge driver the larger and larger blades become. And finally, recyclable, as stated earlier on in the overall objectives that the Catapult has, end-of-life issues and making sure that there's a responsible development path for the tons and tons of material which is being produced to produce blades. That has to be front and center of any blade development in the future. As part of this, we're really looking at this segmented approach. So to go in more depth, conventional blade manufacture is really mold centric. So everything revolves around putting that process through, and there's those ancillary steps basically means that the utilization of the mold function, which is actually just to mold the resin and the composite part, is actually quite low. So all the external or ancillary necessary activities around, you know, dry fiber preforming, adding webs, joining the spars, curing flanges, that basically monopolizes that mold to a point where it's becoming less productive. So if we take a segmented approach where each of these segments basically are produced with their own specific cell. So taking this cell-centric manufacturing approach, we're lowering this bottleneck through a single mold operation approach. So it allows parallel component manufacture, which is a fundamental departure. It also means there's great flexibility in manufacture and more contingency and redundancy. For instance, if there's a delay in process, you're not putting a whole operation in line because of one cell, for instance, is broken down. And more importantly, each cell is configured and optimized for the particular segment being produced. And this is the real heart of the Unblade concept, that the feasibility study that we've undertaken, where really the part is the tool. So we want to produce a modular segment via AM with all the high detailed featuring of structure and aerodynamic outer envelope that we can attain, and we have through an additive manufacturing approach that power to be brought to bear. So specifically, that outer surface provides a surface from which skin reinforcements can be added of a thermoplastic nature, and then basically covered by a surfacing film. Recesses take the primary load paths provided by the spar caps, so effectively internal channels or recesses through which they can be fitted. And essentially those shear carrying members between the spar caps can be topology optimized using additive manufacture to produce shear webs, whether they're locally integrally reinforced by secondary members such as the spar caps could be. And quite clearly it replaces a unitized internal structure that's been topology optimized, replaces a lot of failure prone costly foam sandwich, which is the current build technique. So in a bit more detail, the chief advantages of the AM blade approach that we're looking at, apart from eliminating a very large capex intensive mold set, is the high manufacturing productivity we can get. It's completely compatible with a modular approach to manufacture, similar to an automotive style of manufacture. It allows rapid production changes which are implementable. So if, for instance, there were design changes around one particular aspect of the blade, it wouldn't mean wholesale changes and the engineering lead times required of a blade set to be produced. Obviously, the maximal design freedom is a huge one, which I've touched upon already in terms of the aero design possibilities. But more importantly, it should be recognised the reduced development cycle of the engineering has been reduced as well. And furthermore, client-specific customised blade design would be a lot easier to implement. And lastly, of course, I know I've mentioned before, it's very important though that the material system that we've discussed, that we're looking to use from this concept study, is basically a two-component system. So inherently, it means there's no mixed waste stream, so it's far more easy to recycle, and that's the ultimate aim. So you're having one fiber type, maybe two fiber types, but basically one matrix system to replace a lot of adhesive and metallic structures, or where we can avoid metallic structures. Obviously, for things like lightning protection, we'll still need those metal components, but it'll be basically to a bare minimum. So as far as the Unblade feasibility study goes, there's a structure there that we use which is akin and resembles what a current blade is like, with separate skins being held apart with shear webs, with basically a 3D printed overall module. So basically material properties have been estimated using this approach, and calculated properties for static analysis to give impact on blade mass, basic joint calculations, as well as a final costing of this approach. So starting with the material, we basically use ANSYS material designer for chopped carbon fiber to create a virtual material. And that was based on data of these pre-existing materials. And this data was basically used to produce a gyroid using a representative volume element. So from this gyroid, we could basically change its thickness and its cell size and see how that would compare with conventional materials. So in comparison with with other core materials typically used, and here we've got a graph on the right there showing the specific shear strength of commonly used PVC core materials. And you can see these gyroid configurations we have a clear advantage in its specific shear strength. So it inherently means that for a given mass of material, we'd be able to achieve much higher strengths. So therefore we'd be able to save weight. So in the Unblade costing assumptions we've taken the NREL detailed cost model, and that's been applied to the DTU 10 megawatt reference blade. We've used large scale FFF, as Ollie outlined, to produce those core modules. And basically for the fiber treatment on the outer surface to produce these skins, we've looked at fiber patch placement as the core technology we'd be using. So a lot of those cost assumptions are embedded in the NREL model, has been taken. So things around cost of capital and wages, they've all been taken into account. Now for the fiber patch placement machines, you can see the figure there below. They've been scaled so that each segment is roughly equal mass in terms of the amount of fiber that has to put down. And that effectively means there's a common blade manufacturing metronome. So you're creating the same number of parts within that same time for assembly. So as far as the assumed factory layout, this is a very rough study. So not everything's been taken in really super high level detailed account, but basically these are the assumptions we've used along with that model. So one blade every 21 hours. The factory assumes those 8 segments of roughly equal mass. So those, as you can see on the right-hand side, those blue sections of additive cores that basically feed 20 fiber patch placement machines. And the assumption is those have been used for 21 hours within a 3-shift labor rate. So getting to the important bit, which is the results of the study. As you can see on the left, there's the conventional DTU reference blade, which comes in at around 380k euro. We compared this with 3 scenarios. The first scenario, well, sorry, I'll get to that. So basically using the AM approach, we basically eliminated tooling costs and consumable costs that would be associated with resin infusion, and had clear reductions in maintenance costs, building, labor costs, particularly overhead of labor costs necessarily, and utility costs. And we compared this to 3 situations or 3 variants of the concept that I've shown. The first of which is basically have a carbon-filled AM module. So that simulated material we showed used carbon fiber in a base resin, and that was basically extended throughout the entire blade. So FPP was used to put down the spar caps as well as the skins. And for that, you can see a clear reduction of around 31% in the cost differential between the DTU reference blade. In the second scenario, basically, we've substituted the carbon fiber for less expensive glass-filled thermoplastic resin, but again, keeping all the fiber, including the spar cap, fulfilled by fiber patch placement. As you can see, there's a 36% saving over the conventional route using that route. And finally, we compared a glass-filled AM module with FPP shell only, but having pultrusions basically take over the primary spare, as is the trend these days. And that produced a 52% cost differential over the DTU reference blade. So the findings of the AM blade study, basically the concept does make use of gyroid structures, which are extremely efficient structural form, and they're only possible to produce using additive manufacture. We say 52% over a conventional half shell infusion. The concept eliminates a requirement for a blade model, obviously. But beyond this study, we've also seen, particularly at the outer extremes of the blade, there's a possibility of actually completely removing the skins, which means we'd actually make the process even cheaper because you wouldn't have to actually put a blade skin on. So as long as the selection of the thermoplastic material met weathering requirements and obviously the aero requirements, that could be a further cost saving. And finally, the blade would be reduced to 2 constituent materials to produce the composite. So overall, as a summation, those 6 points, there's basically a recapitulation piece here around the segmented, the importance of the segmented blade design in offering manufacturing flexibility in a cell-centric manufacturing approach. Secondly, using modular components, demonstrating a step change in low-cost blade manufacture, almost akin to an automotive assembly model of production. Thirdly, and most an underpinning tenet is the tool-free blade manufacture possibilities. Fourthly, the design freedom drives multiple innovations across the blade. Fifthly, the potential for mass savings, and finally, the importance of recyclable thermoplastic material and waste elimination. So that's sort of a very rapid overview of where we see the future for blade manufacture using AM. Now, having come to the end, in session 2, we'll look at the opportunities, challenges for future potential immediate application of additive manufacturing in the space. So I'll be talking at 10 past the hour on sandwich cores. Then Ollie would be talking about interlayer adhesion in additive parts. And then finally, we'll have Arjit from Imperial College talking about topology optimization. So if everyone wants to have a bit of a break, and we'll see you back here at 10 past.
Yeah, just a quick reminder there, please post any questions into the chat and we'll try and raise those and deal with them in session 3.
Great.
We'll see you all in 10 minutes.
Cheers.
Right, so it's now 10 past 10, so we're going to restart the sessions. Hopefully everyone's had a chance to grab your coffees now. Again, just a quick reminder, drop any questions into the chat function. Otherwise, I'll now hand over to Mark Forrest, who's going to give you some more information and details on our activities around sandwich cores. So over to you, Mark, if you'd like to start screen sharing.
Thank you. There we go. Good stuff. Welcome back, everyone. Yeah, so the current opportunity I'd like to outline now is around sandwich cores, and this is specifically around how an additively manufactured sandwich core could integrate within the current blade manufacturing resin infusion process, which is used. So it's not what we talked about earlier in terms of the overall building a blade module, but specifically sheet material or a substitute for sheet material. So in doing that, having introduced that, there we go. So initially, I'd like to give some background to sandwich cores and their use in blades, outline some of their issues with conventional cores as they're processed, and finally give a quick an AM manufacturing opportunity overview to it. So it should be relatively quick, so I can leave time for more discussion with the group or any questions brought forward. So first of all, sandwich cores in blades are quite fundamental lightweighting methodology to invoke stiffness in a structure without having an undue weight penalty. So basically, they're used to increase buckling resistance between unsupported panels. So as you can see there, the leading edge and the spar cap, and between the spar cap and the trailing edge, those areas highlighted in blue are the longest sections of skin which need supporting by foam. And the shear webs are shown in brown, but nonetheless, they're all core sections that usually have a weight range of between 50 and up to 300 kilos per cubic meter. In terms of large blade implications, with the NREL cost model, looking at a sandier blade, that's a 100-meter blade, around 8% of the mass is devoted purely to core section, and it's not in proportion to its cost. So for instance, in that particular 100-meter blade, we're looking at about 21% in BOM cost. So it's really disproportionate to the mass of the blade, of the proportion of the blade that's taken up by the core. So for that 100-meter blade, that BOM cost of 21% basically translates to around 70K per blade for a 100-meter blade. So that gives us an upper level of our thinking in terms of the cost to implement or the cost of a solution, the budgeted cost of the solution against the current standard. So in terms of the traditional core material, obviously types that are used in blades, usually PVC, but now more and more so PET is being used, and bolts is typically used, sometimes full length of the blade, but more commonly where the higher compressive loads are taken near the root. Typically they're produced, apart from balsa obviously, by a slab stock manufacturer and secondary high-speed machining. Because it is slab stock, there needs to be a way to conform the core to the local curvature of the mold, and usually that's done by grid scoring. So basically, either in one dimension or in two dimensions for compound curvature, the core is basically sectioned or partially sectioned to allow it to deform across curves. And then on the other side, it's usually scrim bonded to keep a whole panel, increases its handleability and formability into the mold sections. It can also be done by thermoforming, but that's less common. So all these materials, they respond very well to traditional machining, and that's why they've seen such large scale implementation and fairly low costs, because they're using traditional technologies that are well understood, high speed milling, sanding, drilling, all those mechanical subtractive techniques used to produce them. So those secondary operations to the slab stock are basically what kit or third party kit manufacturers do. So they're basically supplied as kits that are pre-numbered and labeled and drop into the into a mold directly when fibers being laid up. So in terms of the process, if you're looking at vacuum infusion with dry fiber skin reinforcement, you see a picture of how these are basically manually placed by hand. So there's obviously a timing element, but also an accuracy implication of doing this by hand. And the type and the density of panel and thickness can change down the length of the blade. So in a particular core kit for a new blade, you'll have a number of different materials of different thicknesses and densities. As I said before, to maintain curvature in the cell, a lot of these edges have to be scored so they can actually conform to the surface of the mold. But the consequence of doing that is basically you have very resin-rich joint interfaces between panels, and also to take the resin which flows into the core as a result of the infusion process. Not only are those perforations taken, but the cut surfaces of the foam, where the individual cells of the foam, as you can see in the bottom right, they're taken up with resin from the resin infusion process necessarily. And that's quite a lot. So you can see there around 5% is taken up by the core by these perforations and cut joints. So it's a very large proportion of blade. So you'd actually have a significant weight saving if that could be minimized, the amount of resin absorption into the core, which is represented by about 2,400 kilograms in that 100-meter blade. So it's not insubstantive. In terms of the infusion behavior, basically when you have a core nested between dry fibers, you basically have to have a way of under vacuum pressure transporting the resin from the top side where the resin infusion medium is, where the transport and vacuum pressure is expressed, to the underside of the mold, between the mold and the core, which is relatively vacuum. If it wasn't for holes, would be relatively vacuum impermeable. And this is basically to make sure that there's no dry spots in the laminate between the mold and the composite being produced. This has quite large implications on the quality, however. So those cut grooves and perforations which are used for flow control to equalize the permeability on either side of the core, their placement, relative size, and periodicity basically change the quality of the laminate you can get on that critical underside of the laminate. So any kind of replacement has to be able to ensure that permeability between the top skin and the bottom laminate skins of the sandwich panel are maintained. So really, we have to be able to transport resin to control the lateral flow as well as the transverse flow of resin in respect to the panel. And so really, it's critical to quality. And the reason why this is so critical, particularly in a sandwich core, is the multiple failure modes that foam cores can fail by. So it's critical to quality, even just as much so as a plain laminate, but because of the extra requirement for adhesion through the core to transfer shear load, it's vital that good adhesive bond is maintained with the top surface of the the core. So as far as additively manufactured cores, we'd propose that you'd basically have a tile. So that tile could be filled with whatever topology optimization lattice cells could be invoked. That would be basically covered as a single module that could be placed into the mold in a discrete position. But it would allow a tessellated approach to kitting the blade and designing the blade for these core inserts. So they'd basically nest together and laid into the mold. And a clear advantage of using additive is that you could really control the tolerance between these tiles very well, almost like a snap fit, like a Lego brick operation where you'd have a very secure joint. You could have strong control over how much resin seeps into that interface. And you could have surface features, for instance, that would be used to control the flow, both on the top surface and transverse to the surface to feed that bottom skin in the regular way an infusion would typically work with conventionally produced foam cores. So whether it's an internal labyrinth of channels required and how they interconnect for vacuum to be expressed through top skin and the bottom skin, that's a major point which has to be considered in this approach. But the other obvious advantage of having additively manufactured cores is the level of integration you can get with the rest of the composite structure and subcomponents you need to attach to the blade inner surfaces. So particularly around subcomponent fixturing points, water drainage channels, for instance, which are required, lightning receptors, but other practical things like placement aids and laminate strengthening. So you could imagine on the top surface or both surfaces, you could have a dimpled surface maybe or a spiked surface that would penetrate the dry fiber laminate stacks to effectively help pin them, locate them, but also potentially aid transverse strength of the laminate, as well as actually providing an opportunity for internal resin flow media to be designed within that body. And that gets back to the point I was making earlier of having separate channels being allowed to transport resin on the top surface and the bottom surface of the core. So there's key questions, obviously, that raises. Firstly, the design elements. What size of core gives the optimum cost and resin uptake? What design geometries give this best snap fit behavior I was referring to? Which geometries give the optimum strength to cost ratio? And how long does it take the foam tile to assemble in place? Are there any advantages over an accuracy, and how can we quantify those over existing methods? Also, as to the materials and process, which surface and internal features offer the best skin infusion quality? And that goes hand in hand with the next one there, is how to best integrate those different infusion strategies, such as flow channels within the designs. And clearly, whatever material this tile is produced from, what's its compatibility against commonly used matrices used in blade manufacture, particularly epoxy, polyester, polyurethane, or acrylate. And lastly, manufacturing approach. Clearly, FFF could be a winner here, but are there other possibilities of which other additive approaches would be suitable? And what are the cost implications of on-site production, whether you go for a supplier model that has to be where you have to ship foam as a kit to an OEM, or would the OEM basically be able to have their own on-site print farm? What are the economics of that? How does the cost modeling look around that? So there's some questions really to provoke thought in the group. And yeah, I'll hand it back to Neil, I think.
Sorry, I couldn't unmute there for a second. Yeah, thanks for that, Mark. So again, some interesting issues raised there by Mark, and again, very happy for people to drop comments in. We're also very interested in any businesses that may be interested in collaborating on future projects going forward. So again, if there's any project ideas here, particular themes that you have an interest in, please do let us know, and we can follow up with you after the event. So I will now pass over to Ollie for his second session looking at laminates. You there, Ollie?
Yeah, I'm showing my screen now. Okay.
Lovely, thank you.
Cool. Yeah, so following from Mark's topic, I'm just going to sort of present an overview of what I think is a good research avenue for AM parts. This is part of a materials sort of theme in this case. However, there's many more areas in materials, but I think interlayer adhesion of additively manufactured parts is definitely a very deep research opportunity for sure. So I'm going to give an overview. I'm going to give a recap of the thermoplastic deposition process and define the concept, and then sort of go on to opportunities, and then the sorts of implications for manufacturing and further projects. So as I talked about earlier, the thermoplastic deposition process is via you're introducing a layer by layer approach of melted thermoplastic material, where you have the interfaces between the beads or the rods that are being deposited, with the extruder following the tool path that is going to gradually build up your part. So I think this is a really simplified view of the situation, but ultimately, say for example, you're producing beads in the same direction. The interlayer bead or the interbead interaction forms inherent immaterial anisotropy. So effectively, the material properties are going to be stronger along the direction of the beads. And so effectively, you have the strength being highest in the direction of the beads and the sort of lowest transverse to the direction of the printed beads. The bonding between the layers it sort of requires like intermolecular diffusion, sort of thermal fusion and polymer interdiffusion. So you have sort of like the initial surface contact of the beads as they're being deposited by the extruder, and then the process of the coalescence of the beads takes place through sort of neck formation, and then you get the diffusion of the polymer molecules in the melt. And then you get sort of randomization, but ultimately, I think if you're essentially manufacturing large AM parts, I think there's a bit of a trade-off going on here. So the interlayer, you need the bead needs to be maintained at or around, or preferably above, the glass transition temperature to be able to get a good surface contact area. So the strength the strength transfers to the beads is derived from this contact, the formation and the coalescence of beads. So effectively, if you're printing a bead if you're printing something that's got too much energy, too much heat, too much thermal energy. If the beads retain too much heat, you effectively have lower viscosity, and the part will start to droop, or you won't be able to maintain good geometric tolerancing. However, sort of on the corollary, if it's taking too long to print, or if your beads, in the case of larger AM parts, if it's taking a long time to before deposition of the next layer or the next bead, and the temperature of the lower of the area that you're depositing on, if the temperature of the beads drops too far below TEG for too long, then you get a poor interface between the subsequent layer. And that's a classic problem with AM thermoplastic materials. So you have this sort of strong plane along the direction of the printed beads, and it's slightly weaker transverse. It's effectively on desktop printers, you get a slight reduction, but on larger AM platforms, you can get big reductions in the interlayer strength. So it presents really a very deep and a very good research opportunity or research avenue in terms of the material, improving material properties. So I think it relies on being able to measure the temperature history of the deposited layers accurately, and among many of the other sort of characteristics of the thermoplastics, highly material dependent and highly temperature dependent. So I think, like I was sort of saying in the previous slide, so larger AM parts with larger AM platforms essentially means that it's taking potentially a longer time prior to the deposition of the next layers, and so this gives rise to the material anisotropy. So if we're too slow, then as I said before, you won't retain enough heat to get a good bond. So I think in the literature there's many approaches. It's not limited to these approaches, and I don't purport to have all the answers to this. But I see this as being a really, really deep research opportunity for, especially in the case of large area additive manufacturing. So Rationale over in Tennessee, whom I just discussed earlier about their big area additive manufacturing system, they used like an infrared laser preheating system just prior to the application of the next bead or the next layers, and they found that this drastically improved the interlayer properties. Other approaches can include sort of the application of through thickness with 3D reinforcements. I believe there's a research group that I think it might have even been Rationale again. They produced sort of strips of thermoplastic in the Z direction that is within the overall build, and that also improved the situation regarding the sort of through thickness interlayer strength. So likewise as well, I think they used a Z tamping platen. So on the extruder, they had this sort of Z tamping platen that sort of beat or vibrated the top of the surface, the sort of melted surface, the melted bead, molten bead, and they found that this improved the interlayer adhesion between beads, encourages the net growth and the sort of sintering process of the beads. Another approach was in the literature was I think this was done on a sort of more of a desktop based system, but I don't see why this isn't applicable to larger AM platforms. But they basically found applied like a sort of coating, a carbon nanotube outer coating on the deposited beads, and applied a sort of electric field and some sort of plasma treatment to effectively kind of weld the beads together. So, I mean, these are just current approaches that are sort of in the literature. It's basically, like, I sort of wanted this to be a bit more of an interactive session, really, but really it was kind of like what the kind of implications of this on the manufacturing approach. Is this, you know, in people's opinion, is this going to go some way to improve the route to market of AM cores, for example, like Mark was talking about? Is this going to facilitate better material sort of certification, so that kind of thing? And can we optimize the design to be able to reduce this effect? So again, going back to the gyroid structures, you know, will that be able to partly go some way to answering this conundrum? So yeah, I think that was kind of it. So this was really just to kind of you know, instigate kind of thoughts in, you know, alternative interlayer adhesion strategies for strength and sort of robustness of the AM parts and coupons and that kind of thing. So yeah, if I can hand back to Neil, that's I'm hoping this will facilitate some thoughts. And again, if this is quite a deep research avenue, and I feel there's a lot of scope for future collaborations and potential proposals coming out of this topic. So again, feel free to get back to me or Neil, and we can take things forward. But for now, let's just instigate some sort of like sort of discussion and figure out if this is a good way to go. Neil, I'll hand back to you now. So that's me.
Yeah, thanks, Ollie. So it's been really interesting content then.
Yeah.
I'm certainly learning a lot of new words here as we're running through these presentations today. A couple of questions coming in, thank you. And again, we'll pick those up following the next presentation with Additive. We are running a little bit ahead of time for a change. So there's plenty of opportunities for questions if people want to, again, post them in the chat. So I'll now hand over to Dr. Ajit Panesar from Imperial College London. That's going to give us an overview of some of their activities around design, machine learning, and topology optimization. So I'll hand the slides over to you, Ajit.
Thanks, Neil. Lovely to have you all joining the session today. I'd like to firstly quickly give a shout out to ORE, in particular Mark, to give me the platform to share some of my work with you all. So for the last about 5-10 years or so, I've been working in the area of design, and easily 5+ in additive manufacturing now, where a lot of my remit has focused on lightweighting, particularly looking at topology optimization implementations for even industrial applications, and more recently looking at applications of machine learning in process as well as design of parts. You would find a lot of the footnotes having some kind of QR code. Should you be interested in the works that I'm going to highlight, you may find these a quick link for the documents. So I'd like to first bring your attention to the center of the slide, which is a lovely compression specimen you can see here. We have already seen stuff that ORE has done on testing of lattices. And I just wanted to highlight that in the at least past 2 to 3 years, my group has strongly focused on looking at functionally graded lattices. So we have been trying to take lattices beyond the single unit cell type, uniform density variation throughout the domain, to more exciting territories, which I'll show you in the next slide as well. And we have done quite a lot of numerical simulation, which is complemented with the experimental investigations like you can see here. So these are digital image correlation snapshots for our compression specimens. And more importantly, we have tried relating them on the figure on the right, which is looking at similar to what would be coming from Gibson-Ashby predictions on ideal stretching dominated, like the ones you see gyroids or Schwarzschild, the more surface-based lattices, to ideal bending, which is the more commonly seen, like the body-centered cubic, the BCC, FCC kind of lattices. And we have shown that through this functional graded lattices, we have been able to tailor the properties and transition between ideal bending and ideal stretching dominated lattices. And as I pointed out earlier, at the bottom right is a link to the paper out here. My pointer is misbehaving a little. And all of this work came about from about 3.5 years ago, for which the link to the paper is again given at the bottom right. This paper has been amongst the top 10 most cited and downloaded works for the last 3 years running. And what you see out here is the culmination of a last couple of years' work, where we have translated some of the capabilities of how to embed lattices into design as well into analysis. So here you see different ways in which lattices can be generated for a part. We also give opportunity for volumetric grading, which means you can take results from likes of topology optimization or a user need and have custom unit cell types, where you can even change the unit cell size as well as the unit cell type within one structure. You can also partition a domain like the one you see on the right-hand side into several subdomains, where you can select where you would like a higher density of lattice or a particular kind of lattice, and it would very smoothly transition between one unit cell type to another. And these are just examples of some unit cells that you see on the left of the screen. The important thing worth pointing out is we care about what AM users want in terms of the outputs, and quite commonly STL files are very notorious to be large in size, and therefore we have given compression algorithms out here which would allow you to reduce your STL file size. And for more advanced users, delving into direct FEE mesh, whether it's Abacus or Nastran, your preferred choice of solvers. So again, this software would allow individuals to try making up simple as well as complicated lattices and do some design as well as testing. And please give me a shout if you would be interested in knowing more about this later on. Next, we have been looking at application of machine learning in particularly combining lattices in topology optimization results. So right in the middle of the screen, if my pointer allows to show to you, maybe I can highlight. Yeah. So here we have been looking at inverse designs, by which I mean, if someone asks us that they would like a particular property, elastic tensor property in the region, how do we know which unit cell would map there? This is the entire premise of this machine learning activity that we have embarked on, where we are looking at inverse design for the topology of the unit cell itself. What this should ideally allow us to do is work towards the right side of the screen, where we have the more traditional grayscale topology optimization results, pair it with what we expect the material properties to be for these lattices. And these are just for illustrative purposes. You can see how lattices should vary within a structure, but more on this in the coming 6 months' time, I suppose. Perhaps if I could bring the attention to the left half of the screen. So this is where we are looking at using machine learning for design. Now, quite commonly, AM parts generally require support structures. And either you can inbuild the support structures within the part, or you produce this as sacrificial elements that you break down subsequently after manufacture. And what you see here out here is using a particular technique called generative adversarial network. It's almost like working with an opponent, where the opponent is helping design these support structures, which are these plus minus 45 elements you see in the bottom half of the screen. Yeah. What this means is once you have your design ready, to make it self-supporting, we will be able to start to embed these elements such that your final part doesn't require any support while manufacture. And now if we shift our attention to the right half of the screen, this is more to do with the process simulation itself. We have very recently embarked on looking at improving the end parts performance by predicting the behavior both on toolpath optimization, so similar to the FDM processes you have been seeing ORE has been looking at, as well as energy kind of transition. So if we were looking at powder bed methodologies or even like wire arc methodologies, how do we ensure that the end part is indeed having the performance as we would expect, and how can we optimize for that? This slide is giving a very nice overview of some of the activity we have looked at, which is trying to take topology optimization to more real-world use cases. So this is an example of or a simulation from our work where we have been looking at remeshing techniques, both for solid as well as void regions, because those who would have worked in topology optimization may be familiar with these terms. But what this means is we are able to speed up compared to a traditional topology optimization code about 10 times. Most conventional solvers like Abacus, ANSYS won't be able to do these things because they are restricted with the unit cell size or the element size you can have between adjoining elements. We only sacrifice on less than 2% in terms of the optimality of the structure, which means it's still really good, but it's much more applicable for industrial use cases. And the point worth giving a shout out here is it still preserves details at the boundaries. So you can notice those members which are relatively important for us on the surface have high number of voxels representing it, which means it's still smooth boundary variations that we're able to capture. And lastly, perhaps if we look at the right half of the screen, this is to do with powder bed processes, where some of the work was looking at efficient packing algorithm. So this allows, similar to some of the work you've seen in ORE, where the cost metric is taken into account. Here we are looking, if you have different sets of parts you want to make, how on one platform for a machine, you can pack them most efficiently so that it's more cost effective for you to manufacture. And now if I could ask you to look on the left half of the screen, where we are looking at, once you have these lattice structures, like the one seen on the extreme left, quite often you do have boundaries which would have loose hanging members in trusses. And this is a particular net skinning technique. It's a more computational geometry kind of approach that we have adopted here, which allows us to make a net around the entire structure, which you see as the middle figure called the net skin, which then helps having the overall structure some level of integrity for those loose hanging members that were on the outside. And again, as pointed out, there are some QR codes should you want to have a look at some of these works. I believe, as Neil pointed out, we are running a bit ahead of time. So if there are any questions, we are happy to probably take it now or a bit later, but I'll pass it over to Neil to kind of give us the next steps.
Yeah, thanks, Ajit. Some really interesting work happening there. As I said, we'll sort of lead straight into session 3 as we're running a little bit early. But we did have a couple of specific questions in for you, Ajit. So maybe if I'll try and relate it to you and then see what answers you have.
Yeah, fine. So I think I can take the last question which came in. So the question was, does the lattice generator use trigonometric approximation for the TPMS? Yes, it does use trigonometric approximations. Yes, it is possible to introduce thickness within a lattice unit cell. So if you wanted to vary the thickness, you can. Yes, for the last work, which was the topology optimization one, we are able to change the ratio between the solid and void differently, which we actually indeed do in our case. I'm happy to kind of elaborate on this later on if someone wanted to kind of dive deeper.
Yeah, I was just going to say, does that answer your question, Chris, or did you want to come back with any other comment? So I'm happy to open things out to the audience now.
Relating to my question about UD tapes.
I was going to come to that one later, actually.
Oh,
I was
sorry.
just.
Oh, it was Chris Kerr, or the Chris. My apologies. I'll butt out.
No problem.
I think we have already received a yes, thanks. So I trust that Chris Kerr probably was satisfied with the quick responses I provided.
Yeah, perfect. And as Adrian was saying, you've got his contact details there. Following the event, we'll also send a link to all the slides for everyone. So again, you can pick up some of those details and contacts. And we'll also post up the PERISCOPE deep dive report. I've got a couple of specific requests that I'll email people back on, but again, we'll make that available on the Catapult website. So we're just going to now move into more of the discussion session. Initially, we have Dr. Alejandro Reyes from University of Plymouth that's just going to jump in and give us an overview of some of the activities they have going on down in the southwest at the moment. And then we'll get straight into everyone's questions. So hopefully you're out there, Alejandro, if you'd like to step in.
Yeah, I'm here. Thank you, Neil. Thank you very much. And thank you very much, everyone, for the presentations. Are tremendously interesting. I actually work in a school of design, and actually seeing what is going on in other areas such as engineering and manufacturing is great. I just wanted to probably mention that we are going through some developments in the southwest around accessibility to facilities and resources for research that could be relevant for this space. We have been in contact with Marinai through Alex Watley as well to share some of those developments, and I guess this is a nice kind of forum to share the fact that we have a recently finished new digital fabrication lab with access to more than 200 different printing materials. If anyone wants to test something or to explore how this technology could help you, even so at scale, even if it's a small test, there is some resource available for that. But more interestingly, aligned with probably with the future directions of research, we currently have been recently awarded 3 robotic arms from Epson, multi-axis robots that would allow us to test parallel kind of cell-based manufacturing options. These arms are relatively small, but again, for maybe de-risking some ideas and testing some concepts. We have 3 robotic arms. We were the only university awarded with robotic arms by Epson in the UK, and is quite kind of high precision machines, same as everything that Epson makes basically, and we are running them in collaboration with our mobile robotics lab in the School of Engineering. So I think that these talks are really relevant because it can help you kind of position this kind of research space in that intersection between manufacturing, robotics, and design, which is a field we are really moving into at the moment. So if there is any industry partner or anyone that might be willing to explore that, maybe local in the Southwest that might be willing to look into that, please just send me a message, or maybe feel free to, I can share my email in the chat window in a second, and I'm happy to take it from there. But thank you very much for giving me a couple of minutes, Neil.
Yeah, no, that's a problem. Thanks for your input there. So we'll now just jump into the questions. I won't be answering any. This isn't really my specialism, but we've got the Catapult team on hand to address those questions for you. The other thing I just wanted to mention in the slightly wider context, some of the other support we can potentially offer through the Catapult is understanding opportunities in the offshore energy market. So while today's workshop is obviously focused on the processes and the materials side, if people do have a wider interest in where the market's going, numbers of turbines we may see developed in the future, some of those locations, again, just give us a shout and we can help you understand some of that market opportunity and when it may be coming along. So to jump into the questions, we have one initially from Ian Faulkner from Fishy Filaments, asking whether the Unblade project considered cost to recycling and output markets for the recycled materials, which could have an impact on offsetting materials costs in terms of future recyclability. I don't know if Mark or Ronnie, you might want to jump in on that one.
Yeah, sure. Yeah, not directly. We do have end of life projects going on, which does a comparison, and we've got bill of materials data and decarbonisation EOL topics covered in going from epoxy to thermoplastics, but it wasn't done as part of that Unblade study. So the answer is yes, we do it, but it wasn't costed in the data that I presented. So that's basically even more conservative view of the cost, because it wasn't factored in terms of the advantage of the Unblade approach.
Yeah, that's great. Hopefully that answers the question there. As I said, a lot of our work at the moment is focusing on floating wind development. So there are some different opportunities in those sector to potentially get a bit ahead of the game in terms of thinking about those life cycle impacts and the materials that actually go into the product at the front end.
Yeah.
So then moving on to our next question, and apologies for any pronouncement, but we have a question from Alberto Vicente that's asking some more questions on the material feedstock that's going into the AM blades. So we've mentioned that pellets offer a higher throughput compared to filament feedstock. And he's asking a question to comment on the feasibility to employ TP filaments reinforced with carbon glass fiber for AM blade components.
Yeah, certainly. So in the Unblade study, we were actually looking at not a thermoplastic extrusion of the same, but we were looking at LEM resin, simply because we can process it. It has much lower viscosity, so it's relatively easy to put third phase short fiber additives, where the glass and the carbon that we had in the study. So from that route, we are looking at pellet-based feedstock systems. That's the kit that basically has been provided by SEAD to us. So it's pellet-based thermoplastic extrusion end effector. But yeah, we're certainly interested in looking at a range of different extrusion technologies, whether they be traditional thermoplastic, like high melt viscosity thermoplastic systems, or liquid-based, two-component UV curables, low viscosity, which again has the advantage of the low viscosity for third phase additives to be imparted. So yeah, does that answer the question? If you want to come online and have a discussion.
Yeah, I'm not. Alberto, does that answer your question, or did you want to jump in with any additional comment?
Yeah. Hello. Thank you for your question. For Jonathan, sorry. Yes, indeed. It gives yes an answer to my question. Maybe the question also wants to include some other remarks that have been mentioned by other person to the chat. It's more related to the use of carbon fiber or glass fiber, continuous carbon or glass fiber reinforced filaments in order to increase strength of the final blade components, instead of using this pellet with reinforced with short carbon or glass fibers. Okay,
yeah. So that leads us nicely into another question, as you mentioned.
Yeah, I'm sorry.
No, that's great. So, Chris Hare, were you there? Did you want to come in and raise your question and any other comment?
Yes, I am here. Yes, and as Alberto says, that's exactly the question, really. Yes, we have an interest in this because we're just commissioning a UD thermoplastic line in the UK. Really interesting discussions by everybody, and clearly this is kind of still early in the development of using this technology for blades. But yeah, UD fibers would potentially offer, higher performance for lower weight. And there are some systems that use continuous fibers. So when you talk about filaments in all your presentations, I assume you're talking about filaments that have some short fiber reinforcement in them. Generally, when we're talking about filaments, they're kind of continuous, but there are some additive manufacturing systems that use continuous fibers, but only in one plane. So you can put down a layer of continuous fiber and then other layers of short reinforced polymer on top of that. More advanced would be to be able to create these things in true 3D. And I'm not sure there's many people can do that outside of using a tool, a very lightweight tool to lay fibers into, as they would do for aerospace manufacturing and prepregs. So there's like a range of possibilities to include continuous fibers, and they might be wide tapes, narrow tapes, all sorts of things that could, I think, be developed for these applications.
Okay, yeah. Did you want to comment, Mark or Ollie? Is that something we've been looking into?
Yeah, certainly. I think to put it in context, yes, I agree, Chris. Eventually, if we can get to drive materials harder and take up options that do necessarily have higher specific strength and stiffness availability that unidirectional aligned fibers afford, then that's the overall technology arc. But I guess Unblade was done in the context of, right, what's available now and what approach we can take now. And I guess the flexibility and the commercial maturity of the technology simply using chopped fiber reinforce, although obviously not as strong as unidirectional, it is accessible now. And in terms of the arc of the technology, I'd say that's one of the attractiveness, one of the features which was attractive in the concept that we came up with, because we're only carrying, you know, secondary loads effectively by this approach, but it allows us that springboard to use, still have skins, for instance, using continuous aligned fiber via ATL or fiber patch placement, FPP. In which case, yeah, we're certainly interested in development of any method, whether it's direct continuous, as you were outlining, Chris, or whether it was those more mature fiber placement technologies that are already here, and simply, not simply, but develop a product that's blade specific, that could be used as a skin via an FPP process. That would be very useful to us, I think.
Yeah, sounds good. And again, very happy to talk more to you, Chris, on this and other activities with the Catapult as they're going forward. There are a number of projects we've got running that we can't really publicise at the moment, so there may be some commercial activities there that are of interest and worth knowing more about.
Okay, thank you.
So then jumping down the questions, so we have one from the Cornwall NHS Trust. I will confess there's a bit of a conflict there. That's come from my wife and her team at Trelisk Hospital. So we do have another number of companies that are obviously now producing waste products. And I think we have quite a lot of interest in the utility of those products in some of the sectors we've been developing. I'm not sure we've got enough detail in terms of the chemical composition of the waste product from the NHS, but was really just chucking that idea out there. They're developing a number of polypropylene blocks. This is a facility they're looking to roll out across NHS across the country. So how they deal with the increased waste streams, particularly from surgical masks and other products. A couple of companies down in Cornwall have thankfully offered their contacts there. But I don't know, does anyone have any other thoughts on the market that may be available for that product, or are we still too early days? I don't know, Mark, if you want to maybe comment first.
Polypropylene, I'd question its suitability for direct blade part manufacture. There certainly could be some substructures at the tip you could implement it, but certainly in terms of weatherability, I'd question its long-term use externally. There are other material systems such as ASA that have far more weatherability for external use, so it would have to be internal use on blade structure, and yeah, that's my main issue with it.
Yeah, no, great. And as I said, thanks to those that have offered to have some follow-up chats with the NHS Trust there. That actually leads us nicely into a question from Ian Faulkner at Fishy Filaments, that's sort of starting to think more about life cycle costs and impacts. And Ian's particular question, when I find it, where are we? So bear with me a second. Yeah, so I think there was interest in research that may have been carried out around accelerated degradation. And I guess it's worth picking up on our understanding of these new materials we're looking at, and whether that lifetime impact is a consideration. This sort of feeds into the NHS question about trying to produce closed loop systems and having that sort of full life cycle recovery. And is that, I presume that's part of the research we're carrying out, Mark, but maybe yourself or Ajit wants to comment on degradation. going to drop it on you, Mark, first.
Sorry, can you repeat? I was distracted for a bit.
Yeah, it was just really understanding whether we're considering degradation of the materials and the effects that will have on future
most
recycling
certainly.
Opportunities.
Yeah, most certainly. In terms of selection of material, it's certainly up there, and their reclaimability is paramount. Whether the final use, it's one thing to say we can extract material. Obviously, the holy grail is to fully recycle blade product, so we could actually still use it even if it's in a degraded form. We could use it. There'd be a sink for its secondary use case, but ideally we want to reconstitute it and use back in blade structures as the first port of call. Secondly, to find it as a second priority, if we can't do that, have an industrial basis to have a good sink of material that we can put that into, rather than go down the waste stream.
And that could produce a significantly different opportunity to what we have with current blade structures.
Oh yes, most certainly. Current blade structures, in terms of recyclability, it's terrible. So anything is an advantage that we could at least reuse the material. Certainly there are initiatives around trying to reclaim fibre, particularly carbon fibre, not so much glass, but it's still in a degraded form. So it's still the case where you wouldn't be able to get the material properties back to where we would need it for primary use structure. But yeah, it's certainly better than going to landfill. So yeah.
Yeah, and again, I think it's probably worth mentioning that's going to become more important with the targets we now have for offshore wind.
Very much so, very much so.
So when you're talking 30, 40 gigawatts, we're now talking about thousands of turbines and blades.
Yep.
So this impact's going to become more effective as we move forward. Lovely, thank you. Again, if I'm misinterpreting anyone's questions, do feel free to jump in and correct me. So I'll now shift down to a question from Anna Carrasco, who's interested in any opinions or information about the responses to the mechanical test of thermoplastics, and how they could exceed the quality and resistance tests to marine environments. I'm not sure if that's one for you, Mark, or Ollie, potentially.
So mechanical tests. So I think in terms of large AM platforms, I think there needs to be definitely more focus in sort of being able to carry out a more standardized mechanical test. Because at the moment you see the current sort of ASTM sort of standards for tensile testing, for example, it can be suitable for desktop-based 3D printing coupons because of the bead sizes is quite small, so you get like a quite a representative number of beads in a given cross section when performing. So it can give you a reasonably good result for mechanical testing. But when you start looking at larger scale sort of AM platforms, the bead size increases somewhat quite dramatically. And so does the size of the defect. So effectively, you're not necessarily getting, so I agree, you're not necessarily getting the correct answer in terms of using standard material characterization standards for, say, just conventional injection molded thermoplastics. So I agree, there needs to be some, there's definitely a research opportunity there in terms of how do we modify existing material standards to better reflect the material properties, whether it be tension, flexural, shear, what have you, in terms of getting a better answer. So does that sort of go some way to answer this, or was this more to do with environmental factors as well? Was that the right, was that a reasonable answer to the question, or?
Yep. Again, happy for you to jump in, Anna, there if you want to, or we'll move on to the next question if that's satisfactory. Okay, a moment's silence. So again, do feel free to come back to us, anyone with follow-ups. Thanks, Anna. I just got your response in the comments. Actually, I think that question leads nicely to one from James Harrison at Blackfish Engineering. And we did pick up a little bit of this from the PERISCOPE research, but just wondered if you could comment on some of the differences when we move away from wind turbine blades and start to look at applications for tidal turbines and potential effects of seawaters on thermoplastics. So maybe Mark or Ollie, again, you can comment on some of the research in that area.
I think a lot of the research tended to, I believe, for sort of tidal blades tended to be a bit more towards metallic additive manufacturing, sort of wire arc type. I think the thing is, it's kind of a you really want to have the strength. It's more to do with the strength. You need a lot more strength, and I think it's substantially quite different to wind blade production. You're building for strength, really, given that the viscosity of the water is many times more than that of air. So it's kind of not sure if that's answering or the question properly, or whether it's just facilitating more discussion. But yeah, I agree. That's for sure up for discussion. Yeah.
Yes, so it could be a bit more research there. Obviously, we're a lot more advanced in terms of wind turbines because of the position of the sector. I think as we see tidal and wave technologies evolve, we can start to interlap some of these research areas. But it's fairly early days on some of those installations at the moment. Again, I don't know, did you want to come back with anything there, James, or were you comfortable with that response? There you go. Thanks, James. Again, do feel free to get back to us at any point otherwise. And that really leads us to our final question at the moment, unless anyone wants to put their hand up or put themselves forward to raise any other issues. So it's again an additional question from Chris that I know you've looked at quite a lot in the past, Mark. So with the sort of evolution of the Internet of Things and increasing numbers of sensors and condition monitoring on offshore turbines, do you feel there's a good opportunity to build in these technologies to new blade manufacturer up front rather than looking at later additions?
Most certainly. But again, it comes around cost, and cost is the biggest driver. There are lots of interesting areas that condition monitoring can be put towards, but yeah, it basically comes down to cost and who pays for it. And a lot of the technologies are sort of split between, just simply from how the industry is fractured, or I should not say fractured, but the way the industry operates in terms of blades, that where the warranty period runs out from the OEM and then the utility takes over. So really, it's identifying that sweet spot between what's in the interest of an OEM to align with and develop that they can offer, and how much you do it as an operational going concern, in which case the utility customer, which is not good for implementation, because obviously to get the most out of these systems, you want to design it into the blade from the get-go, which means you necessarily have to align with the OEM in the manufacture of it. But certainly opportunities around condition health, around structural fitness, around leading edge erosion particularly. That is one area that's right, because so far we have relatively limited capability, or not capability, but limited accuracy in for any one turbine to use a prediction methodology to get to an answer to say what the state of a leading edge is in terms of its health. So if we could have very clever ways of actually determining in situ damage directly, measuring it directly, take a lot of guesswork out and solve a huge problem in terms of maintenance and predictive maintenance schedules being aligned.
Yeah, and I certainly know we've got a huge amount of activity with our operation and performance team on the Leavenmouth demonstration turbine. So I think we're up to 200 plus sensors there. But as Mark's touched on, there's a lot of discussion at the moment going on around how we collect data, transfer data, perform the analysis, and the value in capturing that data. Is it about a system integrated in a blade, or is it use of an autonomous inspection system?
Yeah.
So again, I don't think there's necessarily a correct answer here, but that's something we've considered.
But in terms of the context, of additive manufacturing, sure, there's great scope to design in bespoke featuring in internal structures where every structure, obviously you want to perform as many functions in that structure to make it as efficient as possible. So for every gram of material invested, you want that feature, that subcomponent to do multiple things. So in that regard, it's a very wise thing to consider a separate function like a sensor implementation as part of the initial build.
Yeah. Oh, thanks, Chris. I feel like we should have met now. So that's the end of the questions. So it's the first event. I think we finished a little bit early, but that's great. I hope the technical input was very useful. As I said, following the event, we'll drop everyone in attendance an email with a link to the presentation slides and the previous research work completed through PERISCOPE. We will be looking at options to develop some collaborative projects going forward. So this is one of the follow-up actions we have through the PERISCOPE project. And certainly through March, we're going to be scoping out project proposals to feed into future European funding calls. So again, if anyone in the audience is interested in looking at collaborations with us, or you're interested in talking to us about getting involved in any of your own projects, please do get in touch. You've got my contact details. Mark's are there as well. And again, you'll have the email link and the contacts when we send out the information post the event. So I will leave it there. Again, thanks for all your input. Really, really interesting stuff. And we look forward to potentially talking to you going forward.
Indeed. Thanks, everyone.
Thank you very much.
Thank you.
Thanks all.